So that's where it probably would tend towards
Okay.
that one as well. Let me just do a quick search to see if anything else comes up that's more, I don't know, applicable in this situation. All right. Residuals. So it only applies to the residuals. That's right. That's what it's saying here. That's the errors. The errors are the the residuals.
Yeah.
Again, may be good to get some follow-up from the instructor on like what does he mean by to estimate? Estimating is the regression provides an estimate of the BIs, but it does not require that the BIs be normally distributed.
Yeah.
The errors, though, are what you check. So again, probably okay there. Sorry,
Yeah.
I'm not
That's
giving
like
more.
looking at like the QQ plots.
Yes.
Right. Okay. Okay.
Yes.
Yeah. Got it. Yeah, that makes sense. Okay.
All right. So 23 is also somewhat class specific. It says we should exclude from the estimation of the regression equation any case for which the residual is more than. And so I like a lot of textbooks here, you see kind of like 2 and 3 as being that dividing line. It really is class specific. Do you have any notes on this? Could have even been from earlier in the course where you talk about what is a acceptable standard error.
I think, and maybe I'm remembering this from my high school class, but the number I have in mind is 2. But I can also check on that. But I remember 2 being what I've used in the past. So maybe that was this class.
Yeah. I'm seeing 2 as well from a Minitab software. And that's like what maybe, that's 95%. This is 99.7%, and that's your empirical rule.
Yes.
It really is a little more specific. I guess maybe this is outlier and this is extreme. You got to be careful with the words here also. But I'm not sure. That's a short answer because it really is a dependent on what you guys are doing.
Yeah.
In that class there. I mean, the problem is when something's too far away, they call these points end up being they end up manipulating, for lack of a better word, the regression equation, and they often need to be looked at, in real life, like whether there's an error or something when this was taken.
Yeah.
All right, so let's go to 24. All right, so you're talking about this earlier. The best plot for checking similar variance conditions is the scatter plot of y on x.
I think that's like, I don't know.
It's worded kind of strange. No, did you guys do any QQ plotting?
Yes,
like
we did
to start out?
Yes.
Okay.
So that's what I would assume.
That's where you start, though. And this is asking about, see, it's worded strange. It's like, it's almost, because it should be checking the similar variance conditions with y and x, not the scatter plot.
Yeah.
So we know for sure, like, this is not when you switch them, that doesn't help. You would never look at just a single residual. So, by process of elimination, it is likely the QQ plot here. But Is the teacher a native English speaker or maybe very old?
No, he is this Indian dude with a really thick accent.
Okay, that's where this is coming from then. Uh,
Yeah.
okay, that does help me to know. Yes, so the the QQ plot is the way to determine whether it comes from a normal distribution or not, which is essentially like checking the
Yeah.
variances, and you're looking for it to be on a straight line with no curve.
Yes.
So if you see any sort of curve, you know that's a problem.
Got it. Okay. That makes sense.
25 here.
Okay, the simple regression model. So that's like simple linear regression.
I believe so. That's your just your y equals b0 plus b1x.
Yeah. Requires that.
So the answer comes down to how n is used in the formula. And and by now you've probably figured out that it's never n alone. I believe it's usually like the square root of n in almost all of
Yeah.
these. So if n goes from say like I don't know, if you double n, decrease by half, twice as accurate. Okay. Let me do you have any regression formulas handy? I'm gonna look some up here right real quick.
Let me, I think I do actually. See. Yeah. Oh, I actually don't. This has no regression on it. No, I do not. Sorry.
Okay, so so to be so we'll just kind of use a little bit of elimination here too. To become more accurate, we know that we're going to have to increase the sample size. Okay,
Yes.
and so that's either A or B, and the question is whether it's just simply doubling it works. But if you increase the sample size by fourfold, the square root of 4,
Doubles it.
yeah, like whatever n is, if you multiply it by 4, that's going to be 2 square root n still. So that's another sort of a
Yeah. So
test.
that would be B then.
Yes.
Okay.
It's very rare when it's not it's very rare when it's like 1-to-1, meaning like
Yeah.
doubling this doubles that. It's usually you gotta go by a power.
Yeah. Okay. That makes sense.
All right, so it's just a little slower. Let me get 7. Do you know if the teacher's style, instructor style, is like more of these like which of the following is true? From the first exam.
The test will be 10 questions on the ANOVA. So looking at like the chart that and then 10 of those, and then 10 questions that are more like these multiple choice.
Okay.
All of them will be multiple choice questions, but more like conceptual multiple choice for the last 10.
And do you any like do you think there'll be any sort of like where there could be more than one answer?
No,
And then here, sorry, go ahead.
does there will only be one answer, but none of the above can be an answer.
Okay, and that's where I was going to ask next is like just from a practical standpoint, there's usually a question that is none of the above. We haven't seen that yet in this,
Yeah.
which is a little bit bothersome. And I didn't know if that was the style. So maybe be on the lookout for that, but there's generally only like one of those.
Yeah, this teacher, I like just do not understand, because sometimes there'll be like a bunch of none of the aboves, but other times it'll be an option and there's like nothing. And so
Yeah.
there's like no consistency in this class whatsoever. But there have been times where like none of the above is the correct answer.
All right. Yeah. Just it's always fun. So these which of the following is true here means that there are because there's none of the above, it could be none of the above, but we're looking for something that does work here. Sometimes let's see, so you gotta read them all, unfortunately.
Yeah.
Do you feel like you could rule any of these out looking at them?
I feel like A is not true.
Yeah.
It's just for linear
Because
regression.
yeah, you wouldn't actually use any of these logs.
Yeah, that just doesn't seem fitting.
Okay.
Does
How about
not
B?
require the scattered plot.
So that what that's
Well,
saying is if the
it doesn't need. Oh,
is that okay? Like, would you run a regression analysis on that?
like you could.
Yeah, you could. Okay, so the answer is you're supposed to do like some sort of a transformation before you do
Yes.
do
Okay.
that. In real life, the first thing you do is you plot the data, like whatever assignment you're given.
Yeah.
If you have workplace, you just plot it and see like, what does it look like? And then maybe you do it. So that's why it would be a no, because there is a reasonableness of there being a linear pattern.
Got it.
How about
and
D? I'm sorry, go ahead.
and with simple regression, it's like it's linear basically, like simple.
Yes, it should say
Okay.
simple linear regression.
Yeah.
And it's like there's a word. That's why I think I even mentioned that yesterday. There's a word missing in one of the problems, but
Yeah. Okay, and then the denominator of the estimate of isn't that
like
well
this is
that's
like go
not
ahead.
true because
Right.
it's over root n.
Well, it like it could be n-1 if it were s.
Wait, can you explain that?
That's just going back to your long ago. How do you find the standard deviation?
Oh.
It's the summation of xi minus x bar squared over n-1. And you're right, you do take a square root of that. But for
Yeah.
sigma, it's just n on the bottom.
S over n. Wait, to get what's on the top of that though?
The same thing. The same thing. But
Oh,
this is
got
just me going way back in your class. And then your standard error is, it is s divided by the square root of n.
okay, that's where I was
But
getting it.
that's kind of a different thing here. So
Yeah.
there's no for a couple of reasons. Now the C is very deceptive because we kind of were talking about that earlier. But if you go back up and look, it is the errors that have to be normally distributed, not the and that's
Actual data.
not the actual, not the actual things.
Got it.
So I that's where I was going with this, is like maybe there is a none of the above that you
Yeah.
will see on your test.
That makes sense. X variable default. Yeah, I see that. Oh, and then I think did we do 25? I think we may have skipped 25.
All right, let's take a look here. Yeah, I did do that. Why did I do that? I'll have to go to the video on that one. All right, so the simple regression model requires that the histogram of the response looks like a normal distribution. So that's the Y value.
Yeah, and
Okay.
that doesn't need to be.
No, it doesn't. Yeah, it does not.
So this would just, it's basically the same,
So the QQ plot is,
the residuals,
yeah, and generally there's a linear,
and that needs to be normally distributed.
not
Or
the
no.
QQ plot, the residuals. The QQ plot is generally a straight line, and it will not have a of the
Oh,
response.
looks like a norm. Well, with like, okay, here's where I like don't understand, because this question could be like, does it look like a norm? Is the straight line that the QQ plot is saying, is that indicative of a normal distribution, or like?
Yeah, that's there's some language barriers because the way that QQ plot looks is there's very few points kind of out at the extreme ends, and then more of them are in the middle. So if you were
Yeah.
to draw a histogram of them, you would get a more of a normal distribution.
Yes.
So that's maybe a question for instructor to say, like, if am I looking at the fact that it's a straight line, or the like how much of those residuals is centered?
Yeah. Okay, that makes. Yeah. Yeah, I don't understand. The good thing about this teacher though is like, so after we do the test, we can go back and like ask for points back if, like, okay, on the last test there was a question about what would be the population, and the way
Okay.
it was written was not specific, so I picked none of the above. I emailed him after and was like, I think your question was like written wrong, and
Mhm.
if it was, I would have picked A, but like that was wrong, and he gave me the point. So if there are like inconsistencies in language, which there most definitely will be because everything in this class is inconsistent, it's like easy to go back and he'll give credit for that, which is good.
That's great. And this is one of those, again, like B, A, not sure, because it could be B. D, it's kind of like what you were saying earlier, like you can always do a simple linear regression.
Yeah.
But is it requirement that that it look linear? Like, it's not a requirement to do it. It's like you wouldn't do a regression if it wasn't linear.
Yeah.
So I mean, I'm leaning towards B and then E, but I think it's B, just if you want my,
Yeah.
opinion here.
That's what I would think. But yeah, I have no clue.
QQ plot of the response. Looks like, so that's, again, that's the Y. Why would you do a QQ plot? You would do a QQ plot of X and Y. Yeah. All right. And post exam, I'm happy to help you sort of dive into language things and give you my
Yeah,
opinion.
I
Even,
think I'll definitely do that. Because I'm sure on my last exam, actually the last exam was a bit more like technical than this will be. But even then I'd love to like look over the language and see if I can get anything back just
yeah.
because of consistencies. But okay, yes, that works. Now if we could go over the study guide and just kind of read through the topics.
Sure.
Because like I understand for the most part, but I think there are still a few
All
that I
right.
think
Let's
so like under learning objectives.
okay.
Um
Yeah, let's take a couple of these at a time.
I think for the first, I think starting for chapter 1, starting at like Yeah, that's perfect. Okay. Study guide.
So one way we could do this is you could, for example, like tell me what each of these is, and I could give you like a thumbs up, thumbs down.
Yes.
Another one is to say like, or ask me if there's anything we haven't covered. Specifically like we haven't made a scatter plot, but I think you know what a scatter plot is.
Yeah. No, scatter plot, I can do confident on that, reading it, just looking at the different axes. Correlation coefficient. So that's R. Is that R?
It's exactly R, yeah.
Okay. And that tells us how much, no, R squared tells us how much of the data is explained by
That's right. And
variability.
that's maybe upcoming here. Yeah, that's E. R gives you direction and magnitude. So basically up or down, I'm sorry, positive or negative, and then strength, weak,
Okay.
not weak.
Core direction in here. I'm gonna write that down.
Yeah.
R direction and magnitude. Oh, and that's why this can be negative or positive,
Yes,
and R
exactly.
squared is not.
And usually there's words like weak, moderate, and strong.
Okay. But that line of best fit, that's just your like regression line.
In the case that it has a significance. The other case is if it's not strong, you just use the average, the Y bar in those cases.
Horizontal line.
Yeah.
Yes. And then, okay, this I actually have difficulty with the B0, B1, Y hat, because I did not use those specific variables in my high school class.
Okay.
Um
So the short of it is the population and the hypothesis stuff is going to be Y and then betas, so on like that.
okay.
But your regression equation, is going to be Y hat equals B0 B1x plus B2 x2 and so on.
And so I have written down that B1 is the estimated change in the average value of X when of Y when X changes by 1. Oh, it's the
That's
slope.
right. That's the slope. Yes.
Okay.
That's right. It's a very complicated way of saying the slope, but yeah, that's what it is. We didn't see any questions written like that, but there are test questions where they ask you like to interpret the B0 or sorry, the B1 value. There's one thing here. Sometimes the B0 value like isn't reasonable, meaning like you don't have any data that close to the intercept. Like sometimes your regression is so far out that B0 is
negative, and it's not.
Or really positive. It's not really practical.
Yeah. I do remember that from high school. So in a situation like that, like that just comes into play in like interpretation of it.
Yeah,
right?
if it's like interpret B0 and it's like shoe sizes, like no one has a shoe size of 0. So that would be, you would just say like it's unreasonable, it's impractical.
Got it. Okay.
Situation.
Okay, that makes sense. And so B0. Oh, okay. I don't know.
So
I think I just like wasn't understanding that this is just like a literal line. I don't know why that
yeah,
it's for me.
It's a literal line, exactly.
Okay. Okay, yes, understand that. And then R squared is it the percent of, or it's
Yes.
the
Percentage of
percent
y
of
predicted by,
explained by the X.
yeah, or explained by x.
And so how does that, like, from R to R squared, how does that make it that different? Like, how does it go from, like, showing the, how does R go from showing the direction and the magnitude to then when you square it being it, like, how much of X is explained by Y? Or
Yeah, I mean,
vice-
the idea to kind of somewhat of the answer to your question goes into how these are actually calculated.
Okay.
You want to know the difference between them. But I think I don't want to say it's like I'm kind of avoiding your question because it's a good question, because it's like, why does strength, or I'm sorry, magnitude and direction, why does that like all of a sudden convert
Yeah.
to, because when you square it, you lose the direction. When you square it,
Yeah.
you lose directions. You just know how well it explains.
Okay.
I was going to go another direction, which was to also emphasize that when you're doing multiple linear regression, like let's say you have a B0, B1, a B2, and a B3, and let's
Yeah.
say these you find out your R squared is like 0.92, which is pretty good.
Yeah.
If you eliminate, like let's say you realize like B2 isn't needed, your R squared may end up being the same because B2 doesn't contribute significantly to it.
Okay.
And I'm not sure if you've gone down that direction, but that is typically how R squared is emphasized. It's like, do you need these regression coefficients, or do you get the same same measure of confidence without some of these?
Got it. Okay. Okay. Yeah. That makes sense.
All right.
Um,
How about
then
RMSE?
that I definitely like, I know it's like used for a lot. I honestly have no clue what it actually does. And I think that's why I like get so messed up around it, because I'm like, just don't understand the meaning of it.
I thought yesterday it was like the first question was it asked for the standard error of mu0.
Yeah.
And
And then
that's, so it's like, how do I say this? Like you know how to calculate it from the table from what we did yesterday.
yes.
We want it to be as small as possible. Let me see if there's another interpretation of this that I'm not thinking of. So this is a measure of accuracy. So I think this is a standard. Yeah. Okay. So there's many different forecasting methods that you may come across. Regression is one of them. There's other types of modeling, and this is a way to compare between models. So like the lower is the better.
Okay.
You're not going to do probably any of that in this course, but there's like seasonal trends which kind of go up and down like
Yeah.
that, and there's other types of modeling, and you want to maybe compare between them, but the lower is a better fit,
Okay.
but better fit of the model to the data.
Okay. That makes sense.
All right, let me grab another grouping of these. Okay, G is straight from a question we did earlier.
Yes.
So that it's
So-
again applying the errors or not. Sorry, go ahead. Let me jump in.
This is, yeah, see, like when I see just that, like weird equation thing, I know I can like piece it apart and make it make sense, but I just like don't, it's not the same. So I took AP stats my junior year of high school and like tested out of the first semester of stats here. So like
Okay.
a year and a half later, now I'm taking stats. And so first it's like been a while, and second, that notation is so not what AP stats did. Like I don't think we never use like beta.
Yeah, that's for, I mean, that's just the difference between population and your sample.
Yeah.
You use beta versus bees for that. The epsilon is never used, but it is an error term. And they're just saying that the errors are normally distributed, but the BIs are not. That's the main takeaway from that.
Okay.
So the error, which is the residuals, is normally distributed,
Okay.
but not the coefficients.
Okay. But not, got it. Okay. And is that like this equation? What is it for? Is it for like a regression line?
Yeah, it's for a regression line. Yes. So G, it's for simple regression model, SRM, simple regression model.
And if this had a B2, would that then be multiple
Yes.
linear regression?
Yes. And I think that was also in there, but it was like y I equals beta 0 plus sigma beta I xi, but it's still had the epsilon I normally distributed with mean 0 and sigma squared variance.
Got it. Okay. Okay, that makes sense. And then
So H feels like it's from a PowerPoint slide, the 4 assumptions. You kind of mentioned them order earlier.
yeah,
Independence, normality.
yes, and independence, normality, and randomness. But that also is from AP stats. Let me see if I can find I remember him putting this on one of his slides. So let me see if I can quickly.
And this is a really good question that could be asked,
Yeah.
which is, which of the following. So there's these, depending on the course, there's, like you said, normality, independence, and then there's this homeoscedasticity that may or may not be something you guys are using.
So I have first, so we went through, there's like, okay, yeah, 4, and then, so first 3 remain the same for both simple linear and multiple linear. And so the first is constant standard deviation assumption.
Okay.
So the standard deviation of the error terms is constant and does not depend on anything else. Second is normality assumption. The error terms follow normal distribution. 3 is the independence assumption. The values of the error terms are statistically independent of each other, and the x's. And then for 4, it's the same same assumption for both simple and linear, but you find it in different ways. So the mean of y's is a linear combination of the coefficients and the predictors.
Yeah, there's only in the simple one, there's only one independent variable, whereas in the multiple there are more than one predictor variables, independent variables.
Yes.
Yes.
Okay. So with constant standard deviation, is that like, because I'm used to hearing like, oh, like check conditions, randomness, normality, and independence, but there's no like randomness assumption does, because I feel like standard deviation doesn't take the place of a randomness.
Yeah, the reference I'm seeing here, it says the residuals have constant variance at every level of X. And that's the
Oh, so that
constant.
would refer to like, does that refer to randomness?
Mm,
Or is
well,
that just like not an assumption that's needed, I guess, here?
I think like to me, the randomness is not, I mean, that's not the right word here.
Yeah.
But I'm not sure. Could you give me just 30 seconds here? I need to check on something real quick. All right, I'm back. Trying to think about what is meant by randomness in
Like that your data is taken from a random sample. Like you have,
yeah. I mean that is true.
because that was just for AP stats.
It still should apply here. But that feels like that's more of a sampling issue, like you said, that it comes from
Yeah.
because the residuals being constant variance at every level of X. I mean, that's a calculated thing that you're gonna
Yeah.
see.
Well, I can definitely learn those four. This can be in my brain now.
Yeah. Okay, let's move on to, let's see here, the point estimates and the standard errors of B0 and B1 and their distributions.
So the point estimates, like in a regression, would be the like B0 or plugging
Yes.
in a value. And then the standard errors, like would I have, do you think I'd have to like calculate that?
No, I mean they're in the table. If you look up
Yeah.
at the means for one-way ANOVA, that they're in the table there. These are T distribution variables. I think that's where it's leaning on that. GHI. So if you look here, I'm just going to snip this in. You can see the standard error. I mean, there's a way to calculate it. I believe it's the same as always, but you know, it's the standard deviation formula.
Yes.
For that column, and I don't know that there's much more to say about that. It produces, I mentioned this yesterday, there's typically a T value
Yeah.
in the table.
That's
This one
like
doesn't.
the cutoff.
Yeah, this one does not have it to tell you. And then they also typically have a P value in there to know whether it's significant or not
Got it.
in these things. And that's where I was referring to, like removing variables because they're not significant.
Yeah. Okay. Understand that. And then the
So next one here is the confidence interval for the parameters B0 and B1.
I think that's just gonna be like given in the table. Like I know how to calculate that. So um with the sample midterm, I feel like I understand that.
There's one small thing here that again, that it's both I and J, but notice that you're like you just mentioned, the point estimates are B0 and B1 for beta 0 and beta 1. The confidence interval is on beta 0 and beta 1. It's always, the confidence interval is always done on the population, and
Got it.
that's a small thing.
This part I'm confused about. Okay.
Yeah, so most statistical softwares allow you to provide a value of X, and then there's a a checkbox that says, what confidence interval we want this, and here's the confidence interval. There's a formula for this. It's quite awful, but you can do a confidence interval for, if you know an X, how likely or what the range is that you expect of around that X. So
So is that
let me
like
see.
is this saying like a type 1 error basically?
No,
Or
no, sorry, that's very different. Confidence interval, linear regression. So they have both confidence and prediction intervals for these.
okay.
I'm trying to find one here.
This I'm confused about. Maybe I didn't go to that class.
So like if you have a regression equation, just a really, really simple one, like y equals 2x plus 1, and you give it x equals 3, okay?
Yeah.
The answer is that its prediction is 7 plus or minus some amount. Like we don't know that it's for sure 7. We know that it's between
Yes.
those two values, and there's an equation for that, and you almost never have to do it by hand. Here it
Is it like
is.
the margin of error?
It is, but it's a different calculated value for that. So let me snip this in. It's for forecasted values of which is what we're doing here. We're trying to estimate. So it's your y hat. Like you get a y hat value, but then you have to, based on your confidence interval, you have to multiply by the standard error. The standard error is this down here. All of this comes from your regression table.
Okay.
And that it's a confidence and a prediction interval. They're separate though. The one here is a confidence interval for forecasted value, and then there's a prediction interval. There's sometimes they talk about the prediction interval being wider than the confidence interval.
And why is that?
It comes from the calculation, but it's when you're predicting something, you want to be more careful to give yourself more margin of error when you're predicting versus the confidence interval on the forecasted value.
Okay.
They sound the same, but they're different calculations.
Okay. Yeah, I don't know because like that really wasn't on this sample midterm.
I would agree.
So
I
I'll
guess
ask about that.
maybe ask if this is like a calculation you need to do, or if you or because if you're just reading it from the table, we didn't do that. We just calculate the mean, or we're given the confidence interval. But
Yeah.
here you go. It's right there. Confidence interval versus prediction interval.
Yeah.
So
So I'll ask.
yeah, they're tough calculations. You don't have enough information from you don't have enough information to do it on your own with that
Yeah.
ANOVA table. There's just not enough here to do that.
Yeah. Okay. That I can ask about for sure.
Because
And
you will have to calculate the standard error. Unless he's giving you the standard error, then I guess you could do it.
yeah, and I don't think Did I ever calculate the standard error? I don't think we did.
So that might be the way to ask the question is like, I understand that, confidence intervals and prediction intervals are based on the standard error. If we're not given the standard error, are we going to be asked to calculate that?
Yeah.
All right, now this is something you sent me yesterday by email. I think you had a follow-up email on this.
Oh, yes. Multiple regression. So yeah, that's he said it's like we don't have to know a lot about multiple linear regression, but just like I guess the way it functions.
So you already talked about the assumptions, only the one assumption being different, which is the multiple parameters in there.
Yes.
How is it different? It's multiple independent variables.
Variable.
Yeah.
Um,
And then we talked, I think yesterday there was a question on like whether marginal slopes were less than partial slopes, and I think you're going to ask why that
yes.
is.
Write that down.
Let me look and see which one it was. There's also a question why marginal slope includes 0, which we kind of worked our way around
Yeah.
answering, but I didn't have a good explanation for that.
Do you have the question number?
Yeah, so it's 17 and 18.
Let me just put that down to refer to. Okay. And then how margin? Okay, yeah, that I can all ask.
Right. This is probably a good place for us to stop here, at least for now. Now I know you've got another lesson later